Today we are going to discuss the topic singular value decomposition. A matrix A of the order m by n can be factorized into U, S, V transpose, where U and V are orthogonal matrices and S is a diagonal matrix. To find a singular value decomposition, these are the steps. Find the eigenvalues and eigenvectors of A into A transpose and A transpose into A. Unit eigenvectors of A into A transpose makes up the column vectors of U, and unit eigenvectors of A transpose into A makes up the column vectors of the matrix V. The diagonal values of S are the square root of eigenvalues from A into A transpose and A transpose into A. Let's look into a question. Find the singular value decomposition of the matrix A. And matrix A is a 3 by 2 matrix 1, 1, 0, 1, minus 1, 1. First we can find A into A transpose. The product of a 3 by 2 matrix and a 2 by 3 matrix results in a 3 by 3 matrix. This is the resultant matrix obtained, and in the further steps we will take this matrix as the matrix A. Next we have to find the eigenvalues of this matrix. So our characteristic equation is modulus of A minus lambda I equal to 0. So substitute this matrix in place of A, an identity matrix. Okay, we get this matrix as the resultant matrix. Now find the determinant to find the eigenvalues. Okay, therefore lambda equal to 0, 3, 2. These are the eigenvalues obtained. Next we have to find the eigenvectors. Therefore, substitute each of the eigenvalues in the characteristic equation. Substitute the eigenvalues obtained in equation 1 in place of lambda. First put lambda equal to 0, then put lambda equal to 0 in equation 1, then our resultant matrix will be 2 minus 0, 2, 1, 0, 1, 1, 1, 0, 1, 2. This will be our resultant matrices. Then in order to find the equation, multiply it with the matrix. Therefore, the equations formed will be 2x plus y equal to 0. Multiply this first row with the first column. Okay, 2 into x plus 1 into y plus 0 into z. To get this equation, 2x plus y equal to 0, x plus y plus z equal to 0, y plus 2z equal to 0. These are the equations we have obtained from this matrix. Therefore, we can see that from these equations we can find the values of x, y and z. Therefore, y equal to minus 2z. Since we obtain an equation like this, just put the value. We can have the triad values. Just put z equal to 1. When z equal to 1, y will be minus 2. Minus 2 into 1, minus 2. Substitute the values of z and y in the first equation. Therefore, 2x plus y value is minus 2 equal to 0. Therefore, x is equal to 2 by 2, that is 1. Therefore, we have obtained the values of x as 1, y as minus 2 and z as 1. Therefore, the eigenvector is 1, minus 2 and 1 in place of x, y and z. This will be the eigenvector when lambda equal to 0. Similarly, calculate the eigenvectors for the remaining values of lambda. When lambda equal to 3, substitute the value of lambda in the initial equation 1, which is our characteristic equation. Then we will obtain the matrix this will be our resultant matrix when we put the value of lambda as 3. Okay, similarly find the equations. Therefore, we get the equation as minus x plus y equal to 0, which is equivalent to x equal to y. Then our next equation will be x minus 2y plus z equal to 0, and our last equation will be y minus z equal to 0. From this third equation also, that is from this last equation also, we obtain y equal to z. Therefore, we can see that x equal to y equal to z, which we can take the value as 1 as a trial value. Therefore, the eigenvector for corresponding to lambda equal to 3 will be 1, 1. This is the eigenvector. So, one more lambda value is there, lambda equal to 2. Find the eigenvector for lambda equal to 2. Substitute lambda in the equation 1, our characteristic equation. Then we will result 0, 1, 0, 1, minus 1, 1, 0, 1, 0. This will be the resultant matrix. Here also find the equation. We will get y equal to 0, x minus y equal to 0, which is equivalent to x equal to y, that equal to 0. And every case so here y equal to 0, and the second equation is x minus y plus z equal to 0. Then the last one is the same, y equal to 0, so no need to write that. Substitute y equal to 0 here, therefore x plus z equal to 0, therefore x equal to minus z. Therefore when z equal to minus 1, sorry, z equal to 1, then x will be minus 1. Therefore the eigenvectors are minus 1, 0 and 1 for lambda equal to 2. So we have obtained the eigenvectors corresponding to all the lambda values. Then our next step is to find the unit eigenvectors. In order to find the unit eigenvectors for each of the lambda values, we have to find the magnitude. So when lambda equal to 0, therefore we have obtained the eigenvectors corresponding to each of the lambda values. For lambda equal to 0, the eigenvectors are 1, minus 2, 1. Lambda equal to 3, the eigenvectors are 1, 1 and 1. Lambda equal to 2, the eigenvectors are minus 1, 0 and 1. Next step is we have to find the unit eigenvectors corresponding to each of these lambda values. So first one, when lambda equal to 0, we can find the unit eigenvector. For that, we have to find the magnitude of this vector. Unit vector, we are finding the unit vector as 1 divided by the magnitude of the eigenvector. So 1 divided by, in order to find the magnitude, we are taking the square root of the sum of the squares of the unit vectors, sorry, eigenvectors. That is the square root of sum of the squares of the individual eigenvectors. That is square root of 1 square plus minus 2 square plus 1 square. This will be the unit eigenvector. That is 1 divided by root of 1 plus 4 plus 1. That is 1 divided by root of 6. This is the unit eigenvector corresponding to this eigenvector. Okay. To find the unit eigenvector matrix, multiply the unit eigenvector with the eigenvector matrix. Therefore 1 by root 6 into, write this eigenvectors as a column matrix. Then multiply it with the corresponding unit eigenvector. Then we will get 1 by root 6 minus 2 by root 6 and 1 by root 6. This will be our unit eigenvector matrix corresponding to lambda equal to 0. Unit eigenvector matrix. Similarly, find it for lambda equal to 3 and lambda equal to 2. This will be 1 by root 3 into, therefore 1 by root 3 and for lambda equal to 2, okay, these are the unit eigenvector matrices. And next step is we can combine this unit eigenvector matrices to form our vector matrix U. Combine. Our next step is to write the matrix U. Just combine all the unit eigenvector matrices obtained. Okay, for lambda equal to 0, lambda equal to 3 and lambda equal to 2. That is, vector matrix U can be written as 1 by root 6, or first unit eigenmatrix, column matrix, just write it, minus 2 by root 6, 1 by root 6 as the first column. Then next, for the unit eigenmatrix for lambda equal to 3. that is 1 by root 3, 1 by root 3 and 1 by root 3. Then finally minus 1 by root 2, 0, 1 by root 2. This will be our first constituent matrix U. Next step is we have to find the matrix V. For that, already we have found A into A transpose. Next we have to find A transpose into A and follow the same procedure. A transpose into A, okay, this is a 2 by 3 matrix multiplied by a 3 by 2 matrix. So the resultant will be a 2 by 2 matrix. And this matrix will be taken as the matrix A. Find the characteristic equation A minus lambda I equal to 0. Substitute it here. Take the determinant of this matrix. Therefore, we get the eigenvalues as lambda equal to 3 and 2. Substitute eigenvalues in our characteristic equation matrix, equation 2. For lambda equal to 3, resultant matrix will be 2 minus 3, minus 1, 0, 0, 0. And to find the eigenvectors, multiply with the matrix xy. Then here we can obtain the equation as minus x equal to 0, which implies x equal to 0. Also y equal to 0. Therefore, we have now eigenvectors corresponding to the lambda value, lambda equal to 3. Next, for lambda equal to 2, substitute it in the characteristic equation 2. Resultant matrix will be 0, 0, 0, 1. Find the equation which results in y equal to 0, x equal to 0. Here also there is no eigenvectors corresponding to lambda equal to 2. Therefore, since there are no eigenvectors corresponding to the lambda values, we don't have to find unit eigenvector matrix, and furthermore, therefore the matrix V will be a 0 matrix. V will be matrix 0. Then our last step is to find the diagonal matrix. Therefore, the lambda values we have obtained so far. In the initial step, while finding the matrix U, we have obtained the lambda values as 0, 3 and 2. When finding the matrix U, and for finding the matrix V, we have got the lambda values as 3 and 2. Therefore, our eigenvalues are 3 and 2. Then just take the square root of these values and place the lambda values, square root of the lambda values as the diagonal elements of a 0 matrix to get the matrix S, that is a diagonal matrix. Then matrix S will be square root of 3, 0, 0, square root of 2, and last one more row full zeros, that is our last lambda value 0. Therefore, the diagonal matrix S is obtained by taking the diagonal elements will be the square root of the lambda values, that is 3, 2 and 0. This will be our diagonal matrix. So, for the final step to conclude, U equal to, we have to write all the constituent matrices as the final step. Therefore, our matrix U will be 1 by root 6, 1 by root 3, minus 1 by root 2, minus 2 by root 6, 1 by root 3, 0, 1 by root 6, 1 by root 3, 1 by root 2, and V will be a 0 matrix, and S will be root 3, 0, 0, root 2. This will be the answer.